When we solve systems by substitution, you have to have at least one of your equations with an isolated variable. And in this example, the second equation has done that. The y has been isolated. So what I'm going to do is I'm going to take the y, which is equal to x minus 1, and I'm going to substitute. See that x minus 1? I'm going to rewrite that first equation, but instead of the y, I'm going to substitute the x minus 1. So it's going to look like this. We have 2x, oops, wrong one, 2x minus 3, but instead of the y, we're going to multiply 3 times x minus 1 equals negative 1. So what I have written is the same as my first equation, except I have substituted for y. Now we just follow our steps like we would for solving multi-step equations. I see it has parentheses, so I need to take care of this. I need to multiply, in this case, negative 3 by both terms. That gives us negative 3x plus 3 equals negative 1. Combine like terms. Subtract 3 from both sides, so we can isolate our x. That gives me negative x is equal to negative 4. I need to divide by my coefficient because I want to know what x is, not negative x. And that gives me x is equal to 4. Now remember, this is just part of our solution. When we solve for systems of equations, we're looking for a coordinate. So now I need to take this x and I need to substitute it back into one of the equations. Doesn't matter which one. So I like to use the one where it's already isolated. I find that is easier. So the equation says y is x minus 1. So I'm going to substitute. I'm going to take that 4. Didn't mean to do that. I'm going to take that 4 and substitute it for the x. So instead of x minus 1, I'm going to write 4 minus 1. And 4 minus 1 is 3. So there you have it. Our solution to this system of equations is 4, 3. So imagine if we were to graph both of these equations, those two lines would cross at that location, at 4, 3. That's why we call it our solution. It's the one point that both of these lines have in common. But to make sure that we did it correctly, we have to do the check. And we have to do the check twice, because we have to make sure that the point is on both lines, not just one line. So we get to do substitution again. So we think that the solution is 4, 3, so this is what I'm going to substitute for x and for y. So the first equation, instead of 2 times x, we're going to write 2 times 4, minus 3 times y, but instead of y, we have 3, equals negative 1. Now, if this point truly does lie on this line, we will get a true statement when we are done solving this. So let's see, 2 times 4 is 8, and 3 times 3 is 9. And that's true. 8 minus 9 is negative 1, and negative 1 equals negative 1. There's our true statement. So now we can say with confidence that the point 4, 3 does lie on that first line. But here's the real test. Does it also lie on the second line? So let's substitute. Instead of y, we have 3. Instead of x, we have 4. And let's solve. 4 minus 1 is 3. Because I got a true statement both times, that means that our solution is correct. If I were to graph these two lines, they would intersect at the point 4, 3. But what if both of the equations are already isolated? What if we have them both in slope-intercept form? It could be that they're both written with the x isolated. That's fine too. But when they're both equal to the same thing, we go back to the transitive property of equality, which says if two things, so let me give you an example. This is the example we gave in class. I said if 2 plus 3 is equal to 5 and 4 plus 1 is equal to 5, that means that these two things are also equal because they're both equal to 5. So based on that theory, since these are both equal to y, that means they're equal to each other. So I can write them like this. X minus y is equal to 8x plus 1. And now, the reason we did that is because now we can just solve for x. And then we can worry about finding y after that. So I want to get my x's on the same side, so I'm going to subtract x from both sides. That leaves me with negative 6 is equal to 7x plus 1. And now let's subtract 1 from both sides. I have negative 7 equals 7x. Divide both sides by 7, and we get x is negative 1. So we're halfway there. We need to figure out what y is, because remember, we're looking for a coordinate. So I'm going to take one of the equations, doesn't matter which one, I'm just going to use the first one. So the first one says that y is x minus 6. So let's substitute negative 1 for x. Negative 1 minus 6 is negative 7. So this tells me that my solution is negative 1, negative 7. But how can we be sure? That's right, we have to do the check, and we have to do the check twice. So I've rewritten both of the equations. I'm now going to substitute the solution that we came up with, the negative 1, negative 7, for the x and the y. So this means that instead of y we have negative 7, instead of x I have negative 1. And let's solve. Negative 1 minus 6 is negative 7. We have our true statement.
Sorry, I didn't get that.
My echo doesn't like when I do this. Sorry. In this one, instead of y, we have negative 7. And instead of x, we have negative 1. Let's solve. Remember, you have to multiply before you add. 8 times negative 1 is negative 8. And negative 8 plus 1 is negative 7. We have two true statements, which means that this solution is the point where these two lines will cross. That is the solution. Okay, one last problem. Now when you look at this one, it looks pretty hard, doesn't it? So, okay, yes, there's a fraction. But the other issue is that neither one of these have an isolated variable. So we have to isolate it ourselves. So what I'm going to do is I'm going to take this one, y minus 1/2 x equals 5, and I'm going to isolate the y by adding 1/2 x to both sides. Yep, we just did this in warm-up the other day. This is how we go from standard form to slope-intercept form, isn't it? These cancel out. Over here on the right, we can't add these together because they're not like terms. So I'm just going to write them next to each other, and boom, we have isolated the y. Now, the reason I did that is because I can take this part of the equation and I can substitute it into the second equation. The reason I want to do that is because it lets me focus on solving for x. Then I can go back and solve for y. So here I've rewritten the equation. 3/2 x, oops, I see I made a mistake. It's not 5, it's 7. 3/2 x plus y equals negative 7. So the y is what I'm going to substitute. So we're going to take out the y, and we're going to substitute. Will it let me erase the y? Thank you. We're going to erase the y, and we're going to substitute in the 1/2 x. I am struggling tonight. 1/2 x plus 5. Now, I don't need the parentheses because in this case there's no coefficient there, so I don't need to distribute anything. So we're good. Now I'm going to combine like terms. 3/2 plus 1/2 is 4/2. So that's 4/2 x plus 5 equals negative 7. But hang on, 4/2, well 4 divided by 2 is 2. So I'm just going to simplify this right now while I'm at it. 4/2 is 2, so we have 2x plus 5 equals negative 7. Subtract 5 from both sides, and divide both sides by 2. This just follows our steps for solving multi-step equations. Here we have x. We know what x is. Now to figure out what y is, we're going to take that negative 6, and we're going to come back up here, and we're going to substitute it in one of the equations so that we can figure out what the y is. Now, it doesn't matter which equation we use. We can use the first one or the second one. I can even use this one. And that's actually the one I'm going to use. I find it easiest to use the one that's already been isolated. Okay, so we think that x is negative 6, so I'm going to rewrite this. Instead of 1/2 of x, I'm going to write 1/2 of negative 6. Remember, multiplication is, you can think of it as of. So what I'm saying is, instead of thinking of this as 1/2 times negative 6, which it is, You can also think of it as, what is half of negative 6? Well, half of negative 6 is negative 3. And negative 3 plus 5 is positive 2. So here we think we have our solution. We think our solution is negative 6, 2. So what I think is that if we were to graph both of these lines, that they would cross at negative 6, 2. This one point lies on both of the equations. So let's do our check just to make sure. Okay, so I've written out both of the equations. My solution that I want to check is here. Here's our x, there's our y, and let's substitute. Instead of y, I'm going to write 2. Instead of x, we have negative 6 plus 5. Half of negative 6 is negative 3. And 2 equals 2. True statement. So, but, you know, that only proves that this point is on my first line. I have to prove it's on the other line too. So let's do that. 3 halves times x, which in this case is negative 6, plus y, which is 2, should equal negative 7. All right, let me do this down here. 3 halves times negative 6. Remember when we multiply fractions, we just multiply across. So 3 times negative 6 is negative 18. 2 times 1 is 2. Our fraction bar tells us to divide. Negative 18 divided by 2 is negative 9. So this whole thing gave me negative 9 plus 2 equals negative 7. It works! Negative 7 equals negative 7. Because both of these are true statements, 2 equals 2 and negative 7 equals negative 7, that proves that this solution is part of both lines. It's where they both cross. Okay, that was 3 examples. 3 examples of solving systems of solutions by substitution. I hope this gives you a better feeling for how these are solved, and good luck.